Okay, good morning, gang. Welcome back to MAP2302 Differential Equations. This is our second class meeting. And today we're just going to kind of pick up where we left off last time. So last time we introduced the idea of a differential equation. We saw what it means to verify that a certain function solves a given differential equation. And we talked a little bit about classifying differential equations. I'm going to kind of quickly recap some of that stuff, but then we're going to continue moving forward. We're going to talk today about a theorem that guarantees existence and uniqueness of a solution to a differential equation, a particular kind of differential equation. We're going to talk about what are called initial value problems, first order IVPs, and we're going to talk a little bit about something called separation of variables, which is probably the most important technique that exists anywhere for solving differential equations. We've got this whole big class, and we've got all this theory that we're going to talk about as the semester goes on, and many different techniques. But the truth is that about 80% of the differential equations that humans know how to solve are separable differential equations. And I'll get into what all that means in just a little bit. But first, let's get things moving. Yes, Cody.
Are you doing homework questions for class, or do we have to go to office hours for that?
We can do some homework questions. I've got actually the homework up here. I had a few that I intended to do, but if there are specific ones that you want to see, I think that would be a good way to kind of recap some of the stuff from last time. So give me just a few minutes and I'll call for homework questions. Over here. Oh, this got disconnected. Let's reconnect this. All right. So again, this is MAP 2302 differential equations. And today is the 29th. Today, we're going to do a few things. We're going to recap ODE classification. Something I forgot to mention a second ago, we're going to talk about that uniqueness and existence theorem, and then also a little bit of notation. An IVP, let me zoom in here, sorry. So we're going to recap the ODE classification and talk a little bit about the categories that differential equations, particularly ordinary differential equations, can fall into. We're going to talk about existence and uniqueness of solutions to first order IVPs. And IVPs, you may have heard this terminology before, you may not. These are called initial value problems. If you took Calc 1 with me, then we talked about those in Calc 1, but not every Calc 1 teacher does. And when they do, they don't always tell you what it is they're doing. They just kind of do it. Other big stuff today, we're going to talk about solving IVPs. Solving those particular first order. And we're going to talk about separation of variables. And separation of variables, again, is that technique that solves most of the important differential equations out there that we know how to solve. Not to say it's all of them, and there are many important differential equations where separation of variables is totally useless. But you'll be shocked, kind of as you progress through your mathematical and physics career, engineering career, just how often a differential equation will show up, and you'll be like, what the hell do I do? And it turns out the answer is separation of variables, even with partial differential equations. That is the case. I'll make sure I'm not missing anything that I intended to do here today. Oh yeah, and there's a little thing we need to talk about over here. I had it as a as a note here. We're going to talk about partial derivatives. It turns out that this existence and uniqueness theorem requires something called a partial derivative to even discuss. So that's going to be necessary. And it means also introducing some new notation. But first, let me just go through these things in order. The very first thing we'll do is talk a little bit about the classification scheme. I see Miguel has a question. What's up, Miguel?
Yeah, Professor, the only interpretation I have for partial like partial differentiation is when in calculus 3 when we did 3D space. So yeah, because like you cannot differentiate, like you can differentiate C from X or for Y. So like is there any other interpretation for this class, or that's just the common?
I wouldn't say there's any other interpretation. No, a partial derivative, the way you want to think of a partial derivative is kind of, and this isn't a Calc 3 class, so I'm not going to go into the full detail, but if you think of a function of two variables, so you've got a three-dimensional graph, a function of two variables, his graph is going to look like a surface, like right? And then if you kind of slice that surface along a coordinate axis or
Just one axis. Yeah.
parallel to a coordinate axis, that'll give you a regular 2D graph that we're used to seeing in Calc 1 and Calc 2. The partial derivative is the derivative of that regular 2D graph that you get from slicing the 3D graph. But the geometric interpretation for us is not going to be as important. It's really just going to be, I'll show you guys how to take partial derivatives in case you haven't had Calc 3, because many of the students here have not had Calc 3. And then we'll use that in the process of applying the existence and uniqueness theorem to certain IVPs. Okay. So classifying ODEs, or we'll just say classifying differential equations. This is kind of review or recap from yesterday, so I'm going to move somewhat quickly. You've got two big groups. These are ordinary differential equations and partial differential equations. These we call ODEs. And they're single variable functions. Like the solution to an ODE is a function of a single variable. And then partial differential equations, we call these PDEs. And here the solutions are multivariable. The solutions to a partial differential equation, PDE, is a multivariable function. Solution to an ordinary differential equation, an ODE, is a single variable function. In this class, we focus almost entirely on ODEs. We're going to do very, very little with PDEs. Within ODEs, we're going to talk about linear differential equations versus nonlinear. Linear differential equations, like we said last time, are much easier to solve than nonlinear differential equations. And remember what linearity in this context means. Linear means linear in terms of the variables y prime, y double prime. So you can have x cubes, you can have e to the x, you can have natural log of x. You just can't have e to the y or y cubed or the square root of y. What else did we want to say about these? I know there was one other thing I wanted to mention here. Order, right? So order 1, order 2, order 3 differential equations. This is just the highest derivative. Appearing in the differential equation. And those were the kind of classification schema that we talked about last time. There's one thing that I mentioned last time but didn't write down, and I'm tempted to say it again, but again I won't write it down because it's not something that's relevant to your homework and I want to keep you focused. But that's the difference between a constant coefficient and a non-constant coefficient in the new differential equation. The only reason I'm going back through this is because this is what you need for the first few homework problems, and in case you missed the lecture yesterday or just wanted a quick reminder, you need to be comfortable recognizing when an equation is linear or nonlinear. And remember, that's all about what's going on with the variables y, y prime, etc. And you need to be able to recognize the order. The general form of a linear ODE you can write it in terms of the Leibniz notation. That's what you saw in the textbook and in the notes the other day. You can also write it in terms of the prime notation as an of x times the nth derivative of y plus an minus 1 of x times the n minus first derivative of y. And then you'd get down to something like a2 of x, y double prime, plus a1 of x times y prime, plus a0 of x times y, and this is equal to some other function, usually g of x. So that's your, if you can write a differential equation in this form, then it is a linear ODE. If you cannot write it in this form, then it's not a linear ODE. And the most notable thing here is that, there's no powers of y, right? There's no weird powers of y. Y only ever shows up to the first power, and the same is true of all of its derivatives. Remember that this guy right here, the y raised to the parentheses n notation, that's not the nth power, it's the nth derivative. So this is differentiate y n times, differentiate n minus 1 times, and then you come down to the second derivative, the first derivative, no derivatives, and that's your general form of a linear ODE. Yeah. So Ernesto, that's the question Ernesto asked in chat there. I guess you guys couldn't see it as a DM. That's precisely what I was answering here. So this is the notation for the nth derivative of y.
Will they always appear in parentheses?
Yes. Yep.
Okay.
Parentheses are how you discern, is this a derivative or a power?
Okay.
So kind of, if you look back at Taylor's formula from the end of Calc 2, the Taylor series formula, it's the same notation we use there. Okay. I'll go ahead and say it, but I won't write it down. If these functions, an of x, an minus 1 of x, a2 of x, if these functions are all just constants, numbers, that's what we call a constant coefficient linear ODE. And those are the ones that we're going to learn the most about, but not until later in the term. So this was what we talked about at the start of class last time after going over the syllabus stuff. In case you didn't want to wade through that video, of course, you're going to need to read the textbook to get the details or watch the video from yesterday. Let's move on to talking about partial derivatives so that we can discuss this theorem. And after we get through this theorem and do a quick example or two, Cody, then I'll take some homework questions. Partial derivatives deserve a lot of respect, and you spend several weeks building them in Calc 3. But for us here in differential equations, we just kind of want the quick and dirty version of the partial derivative lecture. So a partial derivative of a function, let's say f of x, y, and z, 3 variables, say, is, I should say, with respect to one of x, y, or z, is what you get when you differentiate the function f with respect to one of those variables treating the others as constants. That's the basic idea. And I know it's just some word soup, so we're going to look at literal examples here in just a minute. But if you have a function of multiple variables, and it could be more than 3, you could have a function of n variables if you wanted, and you want to take the partial derivative of that function with respect to just one of those variables, what you do is you differentiate that function with respect to the variable you're interested in and treat all the other variables as a constant. The partial derivative, so some notation. The partial derivative with respect to x is denoted, it's a curly d, df dx, with respect to y, this would be denoted df dy, and with respect to z, you get the idea, this would be denoted df dz. So you may have seen these curly d's elsewhere in your math lives, or just floating around in textbooks on the internet. If you haven't taken Calc 3, you'll learn all about partial derivatives in Calc 3, the geometric interpretations, the kind of tangent line-like object that is related to these. But for us, you just need to know how to take them. We just need to show you the very basic mechanical thing here. And that is that if you want to calculate, for example, df dx, you differentiate through the function f, treating x as the variable and y and z as constants. So I'd like to look at a couple quick examples here. Let me just, well, we can make a few up, why not? So let's find df dx and df dy for f of x, y. I'll just do a function with 2 variables here, equals x squared sine of y. We'll start with that. We'll do df dx first. Some notation here. Again, there is a differential operator associated with this. So if you want to know how you'd write that, it looks like this. It would be d dx of x squared sine y, and the curly d, as opposed to a regular Latin script d, is what tells you you're doing the partial derivative. So just like your regular d dx, here's your curly d over curly dx, and that means you're going to take the partial derivative of this thing. In Calc 1, if I asked you to differentiate this function with respect to x, you would assume that y is implicitly a function of x. You would need to use implicit differentiation here. But in this case, we're treating x and y as two completely separate independent variables. No implicit differentiation. We're just taking a partial derivative. So what I'm going to do is I'm going to look at x squared times sine y and treat the variable y as a constant. Well, if y is a constant, then the sine of y is a constant, right? If y is like pi or pi over 6 or something, then this is just a number. It's just a number multiplying x squared. So we differentiate the x squared and the sine y would come along for the ride. So this is 2x times the sine of y. And this is just the number 2, not a curly d. On the other hand, if I wanted the partial derivative of f taken with respect to y, I get that by applying the operator d dy. You see me write these d's two different ways. I prefer to write them coming from the bottom like I did here because they look less like 2's, but I find I get a better looking one that way. Either way is fine. If I apply the operator curly d over curly dy to the same function, now I'm going to treat the x's like they're constants, and I just differentiate the y stuff. So if this was like 3 squared times sine y, then the 3 squared would just come along for the ride as a constant multiple, and I'd differentiate sine y to cos y. So this would be x squared times the cosine of y. Simple enough, right? Nothing too bad. And all your chain rule stuff, all of your other differentiation rules and tricks apply here in the same fashion. Questions about either of these? Okay, one more example of partial derivatives, then I'll show you the theorem, and then we'll do some homework questions. All right, let's make life a little harder on ourselves. Here my function f is the tangent of x squared plus y squared times e raised to the power of x minus y. And again, I want to find df dx and df dy, the partial derivatives taken with respect to each of the two independent variables here. Let's do df dx first. Okay. I want to calculate df dx, the partial derivative of this function with respect to the variable x. I'm just going to treat y as a constant. I'm going to pretend like y is just a number and differentiate through this thing using the same techniques I would in Calc 1. I'm going to need some chain rule when I go to differentiate each of these pieces on their own. And I'm going to need the product rule because this function overall, kind of the outwardmost thing going on here is this product. So first I would differentiate the tangent of x squared plus y squared and leave e to the x minus y alone. And then I will leave the tangent of x squared plus y squared alone and differentiate e to the x minus y. And each of those will be a partial derivative. The derivative of the tangent function is secant squared. So here I'm using some chain rule. I leave the inside alone. And by the chain rule, I need to multiply by the derivative of the inside. And again, that's a partial derivative. I'm taking the partial derivative of x squared plus y squared with respect to the variable x. So I treat the y squared as a constant. If y squared is a constant, then its derivative is 0. So the partial derivative of the inside here is just 2x. That's what I get differentiating this first piece. And by the product rule, I need to multiply by e to the x minus y, left alone. And now to this, I'm going to add what I get when I leave the tangent of x squared plus y squared alone. And multiply that by the derivative of e to the x minus y, which is another chain rule thing. So the derivative of e to the x minus y taken with respect to x is e to the x minus y times the derivative of the inside. Again, taken with respect to x as a partial derivative. So the derivative of x minus y, partial derivative of x minus y taken with respect to the variable x is just 1 minus 0. The derivative of the y would again be 0 because it's a constant, and the derivative of x is 1. So this is just going to be multiplied by 1. So here is df dx. I want you to take a good second here. Make sure you're comfy with where every one of these pieces is coming from. I can annotate a little bit. You can add these annotations if you want. If you don't want, you can leave them off. This is what we get by taking the partial derivative of just the tan of x squared plus y squared using the chain rule. And over here, this piece is what we get by taking the partial derivative of e to the x minus y. And each one of those little pieces involves some chain rule. So you've got a product rule and a chain rule going on. Questions about this one?
So the 2x is just gone on the secant square?
Make sure I'm understanding. The 2x right here?
Yes, wouldn't that be a constant too?
Well, I'm differentiating with respect to x, right? So remember how the chain rule works. I differentiate the outer function, leaving the inner function alone. That's the secant squared of x squared plus y squared. And then I multiply that by the derivative of the inside. So if you take the partial derivative of x squared plus y squared with respect to x, the y squared differentiates to 0. That's a constant. The x squared is not a constant though, right? I'm differentiating with respect to x. So the derivative of x squared plus y squared taken with respect to x is 2x.
Oh, right. I got confused. Never mind. Sorry.
No worries, no worries. A quick little note on notation here. There's a way better notation for this. F sub x. You may see this in different places. I don't think your book uses it, but if you end up watching videos or doing anything like that to help bolster your experience here, f with a subscript x is the same thing as df dx, partial d, f partial dx. I prefer this notation, but your book uses this notation. Okay, other questions on this derivative? I know that these differentiation skills might be a bit rusty, and this is a tricky example, so I'd really love to hear if there's anything else on any of your minds. Don't be shy. Going once. Going twice. Sold. Okay. Let's go ahead and calculate curly df curly dy, the partial derivative of f taken with respect to y. Same sort of thing. I'm going to jump in here and differentiate this bad boy using the product rule. And then within my product rule, I'm going to need two little chain rules. There's a lot of symmetry. So again, I'll have the derivative of tangent of x squared plus y squared times e to the x minus y plus tangent of x squared plus y squared times the derivative of e to the x minus y. Differentiating the tangent, I get secant squared of x squared plus y squared. And then by the chain rule, I need to multiply by the derivative of the inside. This time it's a partial with respect to y. So I'll be multiplying by 2y. The e to the x minus y just comes along for the ride. The product rule. And now I'll have tan of x squared plus y squared over here being left alone. And I'll multiply by the derivative of e to the x minus y. And this time that derivative is being taken with respect to the variable y. So it's going to be e to the x minus y times. What is the derivative of x minus y taken with respect to y? What's the partial of the inside?
-1.
Yeah, excellent. -1. Beautiful. Thank you, Mila. So this is my partial with respect to y. And again, if you want the annotations, this piece right here, it's coming from the chain rule when we calculate dy of tan x squared plus y squared. And this piece is coming from dy of e to the x minus y. And of course, the kind of superior derivative notation for the guy we're looking at in the second line is f sub y. All right, so these are partial derivatives. These are partial derivatives. And again, there's some beautiful geometric interpretation. If you take your higher dimensional graph, you slice it parallel to one of the coordinate axes, you look at just the graph that you have along that slice, that's a regular 2D graph. The partial derivative gives the slope of the tangent line of that 2D graph. It's a special case of other directional derivatives. You'll learn all about that stuff in Calc 3 if you haven't already. But for this class, I just need you to know how to calculate partial derivatives. And this is how it's done. If you want to calculate the partial with respect to x, treat everything else as a constant. If you want to calculate the partial with respect to y, just differentiate the y stuff normally and treat everything else as a constant. Last call for questions on how to calculate partial derivatives or these particular examples here. All right, then we're ready to talk about the existence and uniqueness theorem. I guess first I should tell you what an IVP is, because that's the object the theorem pertains to. I believe this is the start of the next section, right? This is the start of 1.2. All of the classification terminology stuff is a part of 1.1. The partial derivative stuff isn't even in the textbook. They're assuming you know it from elsewhere. So we're beginning now section 1.2, which is on initial value problems. We're going to be focused on first order IVPs, but there are some other IVPs that are meaningful as well. I don't believe your book stresses about those. So, I don't know, they talk about second order IVPs a little bit. All right. A first order the abbreviation for these is IVP. First order initial value problem is a differential equation that looks like this. Your regular derivative, dy dx, is equal to some combination of x and y, and we're going to write this as f of xy. So this is the ODE, this is the differential equation. You're trying to solve for not f, but the function y in this, like in all the other differential equations we've looked at. The thing that makes it an initial value problem, though, is you're given some initial conditions. So this is the differential equation, and these are called the initial conditions. We're going to be focused primarily on first order IVPs. Second order IVPs are the same thing, you kind of just do it again. But I'll go ahead and show you technically what a second order IVP is. This is something like d2y over dx squared is a combination of x, y, and y prime. And here, because you've got an order 2 differential equation, you actually need two different initial conditions. Y prime of x naught, right? So again, these are the initial conditions, and this is the differential equation. In practice, these don't look so scary. You just actually have some combination of x, y, and y prime on the right-hand side, or some combination of x and y on the right-hand side. It doesn't look as abstract when you look at a particular one. But trying to describe them in general is one of the challenges with ODEs. The notation gets a little hairy. You've actually seen things like this, especially if you've taken physics 1. Anytime you're using F equals ma to come up with the position function for some kinematics, particles in motion, whatever, you're solving a second order initial value problem. You're given the second derivative of your position function, and then you want to recover the position function itself. Well, here you're given the second derivative of your function y, and you want to recover y itself. Sometimes you can solve these either first order or second order just by integrating on both sides, right? And you get a constant when that integral is done. And the way you sort out the value of that constant is by plugging in some particular information. That's the initial conditions. So in physics, when you take your F equals ma and you integrate twice to get from your acceleration function back to your position function, you get two different constants, and you have to plug in two different bits of information to solve for those particular constants. That's the two initial conditions you see here. Okay. I'll go ahead and show you a simple example of an IVP. Pick one that's not super intimidating. This is a first order IVP. And I'll write it in terms of the Leibniz notation here. We'll say dy dx or y prime is, yeah, what the hell, is just equal to y. And together with the initial conditions that y of 0 is equal to 3. Mathematicians have a funny word for problems that you can just kind of see the solution of. We say you solve them by inspection. We actually saw this ODE yesterday. What was the solution to this ODE?
Y equals C e to the x.
Very good, right? We're saying dy dx is equal to y, or the derivative of the function is equal to the function itself. We know we've seen that the general solution to the ODE is y equals c times e to the x. So remember, this is the differential equation. The collection of the differential equation with the initial conditions is the IVP. So without the initial conditions, we don't have an IVP, we just have a regular differential equation. We've seen that the most general solution to this ODE, this differential equation, is y equals c times e to the x. To solve the initial value problem above, we need to determine c. So you take your solution function and you plug in the initial conditions. Since y of 0 is equal to 3, we get 3 is equal to c times e to the 0. All right, when you plug in x equals 0, your function should be outputting 3. Now e to the 0 is just 1. So c is equal to 3. Hence, the solution to the IVP is y equals 3 e to the x. Any questions on what we just did there? I would go as far as saying you've all done this before. I think everybody has done this in Calc 1. Whether you called it an initial value problem then or not, I'm not sure. It depends on your teacher. But I think everybody has solved problems like this before. Certainly there are more complicated ones, and I'll show you how to solve those. Separation of variables is one of the big tools for solving those more complicated ones. But for now, I'm just trying to get you comfortable with the lingo, right? The vernacular. So the differential equation together with the initial conditions is called an initial value problem. The differential equation has infinitely many solutions. This isn't one function. This is an infinite family of functions. For every real number c, you have a different function here. Negative e to the x, negative 5 e to the x, 2 e to the x, 3 e to the x, 10 e to the x, pi e to the x. This is infinitely many solutions to this differential equation. But as soon as you specify an initial condition, we have a unique solution. A single function that satisfies this IVP. And that's a big deal. One of the largest kind of challenges in differential equations is figuring out when a particular differential equation or initial value problem even has a solution. And if you find a solution, how do you know it's the only solution? How do you know there aren't a shitload of other ones? That's a question we're going to bump up against again and again through this semester. In the case of first order IVPs, we're lucky. We're lucky in the sense that there's a theorem that guarantees the existence and uniqueness of a solution. So that's what I'm going to show you now. Maybe before, hang on one second. So we'll do this in purple. Let me go ahead and write down what we just said. The ODE dy dx equals y has infinitely many solutions. So here, let me draw a few of them. Here's one solution, that's e to the x. Here's another solution, 3e to the x. Here's another solution. Negative e to the x. And there's many, many more, right? There's actually infinitely many solutions. I could fill this plane with curves, each of which satisfies the original ODE. But only one of these satisfies the initial condition. Only one solution curve satisfies y of 0 equals 3. All the others have different y-intercepts, because if you change that number c in front of c times e to the x, you change the y-intercept. Are we feeling comfortable with this idea? So that's what we mean by uniqueness. Existence, is there a solution? Yeah. Uniqueness, is there one solution? The answer to is there a solution to this differential equation is yes, many of them, infinitely many. The answer to is there a solution to this initial value problem, that same ODE together with the initial condition that y of 0 is equal to 3 is yes, and there's only one. One other comment here before we give the theorem, and that's that you'll notice all of the solutions have the same horizontal asymptote. As you wander off to the left, all the solutions to this differential equation tend towards 0. That's a special observation, and that's somewhat important later in the semester, but we'll talk more and more about that. Now it's time for us to give the theorem. If for no other reason than because you need to know how to apply the theorem in your homework, but also to helpfully satisfy this deep philosophical issue you should have with these problems, and that's that I don't even know at the start whether there is a solution to the problem I'm working on. All right. Theorem. existence and uniqueness of solutions to first order IVPs. Let R be a rectangular region in the plane. In the XY plane. We could say like A is less than or equal to X is less than or equal to B, and C is less than or equal to Y is less than or equal to D. So I've got a rectangle in the plane. And assume the point x0, comma y0, that initial condition point, is in the rectangle. Right, lies in the interior. If both f of xy and the partial derivative df dy, if both of these are continuous, on R, everywhere on that rectangular region, then there exists a unique solution to the IVP dy dx equals f of xy with the initial condition that y of x0 is equal to y0 for on some interval I contained in AB. That's the theorem. I know it's a lot of word soup, so I'm going to draw some pictures and try to help you understand, see it in the context of the example we just did. But basically, if you're given an IVP, initial value problem, first order IVP, and you want to check to see whether there is a solution and whether that solution is unique, you can verify that there exists a rectangle on which the function f and its first partial derivative taken with respect to y are continuous. If the function f and its first partial with respect to y are continuous on some rectangle, then kind of along the x-axis within that rectangle, there will be an interval on which there's a unique solution to the IVP. Basically, if f and df dy are continuous, then you've got a unique solution. That's the way to remember this theorem. All the other stuff is a little bit extraneous. Details matter in mathematics, but this is not a proof-based class. This is not a class where we're focused so much on those details. All right. Let's contextualize this a little bit. Where can we look at something? So, no, we don't want something so complicated. Let me look at one of the, I guess this is a good place to look at a homework problem. So we'll start the transition here. I'm going to grab one of the problems from your homework that deals with this theorem. I'll do that as an example. And then we can spend a little bit more time talking about homework problems. So and Cody, and if others wanted to see particular homework problems, we can do that. Here's one that I had in mind, number 12. You've got a differential equation. Oh, let's see. No, I'd like to do one with specified IVP. Determine region of the plane person passes through the point. Do they specify x naught, y naught here? would have a unique solution. Passes through a point. It's not one in that region. Do we have one that specifies? No. Okay, that's fine. Yeah, we'll go ahead and do 12. I like 12. So here is the first order differential equation, and they haven't specified initial conditions because they want us to come up with a rectangle in which we can guarantee a unique solution. Let me move this over here. We can keep it somewhere it's visible. So identify a region such that the differential equation 25 minus y squared times y prime equals x squared would have a unique solution as an IVP, or sorry, as an IVP if initial conditions are taken from that region. And certainly there's more than one right answer here. That's why WebAssign makes this a multiple choice thing. So only one of the regions they specify will be correct. But in practice, we could come up with many regions. And usually you want to come up with the largest region possible. But let's just see if we can understand this. First things first. This is not written in the form dy dx equals f of xy. This doesn't look like this. So before I can apply my theorem, I need to rewrite this differential equation in the form that the theorem discusses. So 25 minus y squared times y prime equals x squared is equivalent to y prime equals x squared over 25 minus y squared. All right, or you could write that as dy dx if you wanted to. All right. So my function f of xy is this guy. And that's a function of two variables. And again, if you haven't taken Calc 3, you might not be 100% comfortable with what it means for a function of two variables to be continuous. But the intuitive thing that you know from your previous math classes is correct. This is a rational function. It's a ratio of polynomials. You just have a polynomial and different variables, top and bottom. Rational functions, you know, are continuous as long as their denominator is non-zero. So where do we need to watch out?
Five and -5, or y equals 5 and -5.
Excellent. And I'm glad that you clarified there. All right. Now I'm using a funny bit of terminology here. I said along y equals 5 and y equals -5 because those aren't points. Y equals 5 and y equals -5, those are lines. So as long as you avoid the lines y equals 5 and y equals -5 in the xy plane, this function will be continuous. Now we need to look at the partial dy dx. I'm sorry, not dy dx, df dx. I'm so sorry. Df dy. Oh my goodness. Yeah, sorry. So our theorem says if f is continuous and df dy is continuous on some rectangular region, then we have a unique solution. So we've just checked that f is continuous everywhere away from these two lines. Now we need to look at df dy and see where that is continuous. So if I'm going to calculate the partial derivative df dy, I need to apply the differential operator ddy to my function. And the idea here is that the x's are treated as constant. So the x squared is actually going to pop out. It's like a constant multiple. Maybe I'll be really verbose about the algebra just to make sure everybody's comfortable. So this is x squared times 1 over 25 minus y squared. All right, that's how fractions work. And then that x squared can be treated as a constant multiple. So that would be x squared times dy of 1 over 25 minus y squared. And now we can differentiate this like normal. Treat this the same way you would a function of a single variable because there aren't any more x's inside there. So this is 25 minus y squared all to the negative first power. That's how I'll do this, not using the quotient rule because the quotient rule sucks. So I'd say this is x squared, one more silly step here. All right, so we'll use the chain. I'm going to get x squared times -1 times 25 minus y squared to the -2. That's differentiating my outer function. And now I multiply by the derivative of my inner function, which is -2y. I suppose I should put this guy in brackets. All right, so there's my partial derivative, df dy. I'm going to simplify it a little bit. I've got a negative times a negative here. That's going to be positive. I've got 2y over 25 minus y squared squared. So altogether here, this is going to be 2y x squared divided by 25 minus y squared quantity squared. This is df dy. I don't necessarily expect you to show this many steps in your differentiation. Like, I think these 3 steps are all fairly obvious. And if you jump straight to like this and then this, I would be totally fine with that on a test. I'm just trying to help out anybody who's still warming back up. Any questions on the derivative calculation here? Okay. Again, this is a rational function. This is a ratio of 2 polynomials. So where is this derivative discontinuous?
Along y equals -5 and +5 again.
Same places, right? Which is continuous aside from along y equals -5 and y equals +5. Okay. I'm going to draw my XY plane now. Here's the line y equals 5. In the XY plane. Here's the line y equals -5. So if I take any rectangular region within these, like kind of within this window here between these two guys, any rectangular region that does not touch those two lines and pick my initial conditions from there, I will have a unique solution to the associated IVP. So I can take my rectangle anywhere in here. Rectangle anywhere in there satisfies the theorem. The nicest thing to do is to take the whole damn thing. So this is an EG, sorry, my pen died a little bit. EG, for example, if I take R to be the rectangular region, X comma Y. Now, do we want R to be a closed rectangle? I think we do, yeah. So here's a little subtlety, right? If you look back at that theorem, the inequalities that define the rectangular region R were weak inequalities, less than or equal to. So we want to use a closed rectangle, not an open rectangle. So I'll go ahead and specify one. I could say, you know, negative, we'll say -10 is less than or equal to X is less than or equal to 10. And -4 is less than or equal to Y is less than or equal to 4. So that would be like here. So if I take my rectangle to be this, for example, and I pick my initial conditions from anywhere in that rectangle, I will have a solution to the IVP, at least on some interval within that rectangle. Let's go back and look at the problem as it is in WebAssign. See what options they provided us. They said, you know, they want the derivative here, df dy. And then they give us a few options to pick from for a region. Why does this keep, sorry, my mouse is messing up. A unique solution exists in the regions y less than -5, -5 is less than y is less than 5, and y is greater than 5. A unique solution exists in the region consisting of all points except 0, 5 and 0, -5. A unique solution exists in the region y is greater than 5. A unique solution exists in the whole xy plane. A unique solution exists in y less than 5. Which one of these would be correct?
The first one.
Yeah, very good. Right? As long as we stay away from these two lines, will have a unique solution. So I could take a rectangle from any region in here, any rectangle in here between -5 and 5, or up here, or down here. Now, the particular example I chose to fit the theorem happens to lie from this middle region, which is this guy, the -5 is less than y is less than 5 region. But I could have also taken it from the region at the bottom or from the region at the top. So you pick your favorite rectangle in any of those regions, pick a point from within that rectangle. That point, x0, y0, would be your initial conditions, and the associated IVP is guaranteed to have a solution within that rectangle. In practice, what I'll ask you guys to do is calculate your derivatives, tell me where the function f and its first partial derivative are continuous, and then I'll ask you to specify any rectangle. Specify any rectangle from which we could take our initial conditions such that we would have a unique solution. So here, like on a test, a correct answer would include the following things. Correct answer would include the calculation of this partial derivative, telling me where this is and is not continuous. Would include telling me where the original function is or is not continuous, and then specifying a rectangle. All right, those three things I would want on a test. Tell me where the original function is continuous and discontinuous, calculate the derivative and tell me where it's continuous and discontinuous, and then specify a rectangle. Any questions about this guy? I see Miguel's got his hand up, but I think that might be from earlier. Is that from earlier still, Miguel?
Yeah, it was from before.
Okay.
Sorry.
No, don't be sorry. Don't be sorry. Any other questions about this particular example where we're using the existence and uniqueness theorem? Okay. All righty then. I'd like to open the floor to some homework questions then for a moment. That is something that I think at least one person asked for. I think Cody said he wanted to see some homework problems. And then we're going to talk a little bit about separation of variables. So let's do it this way. If there is a particular problem from the homework set that you would like to see or discuss, go ahead and type the problem number in the chat. I'm still not seeing anything there. I'll give just a few more seconds.
I had a question on number 6.
Number 6, okay. So we want to verify that the given function is an explicit solution of the differential equation. Assume an appropriate interval for the definition of each solution. So they give us a differential equation and they give us a function, and they want us to show that this function solves this differential equation. They're breaking it down into steps. They want you to calculate y prime and y double prime. And then they're plugging in part of it for you here. They've got the 25e to the 4x cos 3x. That's 25y. That's the very last term. So in this box, they want the y double prime minus 8y prime. I'll go ahead and run through this. So it's homework 1, problem 6. I'll write the problem down. Show that y equals e to the 4x cos 3x solves y double prime minus 8y prime plus 25y equals 0. Just for fun, practice classification, the ODE in question here, this is an ordinary differential equation. It's linear. It is a constant coefficient equation, and it is of order 2. So this is a second order linear constant coefficient ordinary differential equation, and it's what's called a homogeneous equation, but we'll talk about that later. So to show that this is a solution, I just need to plug this in to this differential equation. And in order to do that, I'm going to need to know y prime. So this would be a product rule derivative, regular ddx derivative of e to the 4x cos 3x. To do that, I'll differentiate e to the 4x. That's 4e to the 4x. That's a chain rule. Leave cos 3x alone. And add to that what I get when I leave e to the 4x alone and differentiate cos 3x. The derivative of cos 3x is negative 3 sine 3x. We can clean this up a little bit. I would say this is e to the 4x times 4 cos 3x minus 3 sine 3x. All right, so there's y prime. We also need y double prime and y prime prime, which is what we get when we differentiate y prime. And that's again going to be a mixture of product and chain rules. Okay, if I give myself enough space here, derivative of e to the 4x is still 4e to the 4x, or e to the 4x times 4. And I'll leave this piece alone. And then I need to add to that, all right, plus here, what I get when I leave e to the 4x alone and differentiate the 4 cos 3x minus 3 sine 3x. Derivative of 4 cos 3x is a chain rule derivative. It's going to be negative 12 sine 3x, because the derivative of cos 3x is negative 3 sine 3x. And then the derivative of this minus 3 sine 3x, that's going to be minus 9 cos 3x. Okay, so let me write y double prime out in a single line and try to simplify it. That's 4e to the 4x times 4 cos 3x minus 3 sine 3x plus e to the 4x times negative 12 sine 3x minus 9 cos 3x. So here is y double prime, and we can clean this up. I can factor out the e to the 4x, distribute this 4, combine my like terms. This is e to the 4x. I'm going to distribute this 4 here and get 16 cos 3x minus 12 sine 3x. And then here I've got a minus 12 sine 3x and a minus 9 cos 3x. And the sines and cosines can go together, right? Cosines, I've got 16 cos 3x minus 9 cos 3x. That is equal to 4x. 16 minus 9 times the cosine of 3x, which is 7. Cos 3x. And then the minus 12 sine 3x minus 12 sine 3x is minus 24 sine of 3x. All right, so there's y double prime, all nice and simplified. So now that I have y prime and y double prime, I can plug everything into this differential equation and see if I get a true statement. Hopefully I do. Let me put that down here. So my differential equation, or at least the left-hand side of my differential equation, is equal to y double prime, that's this piece, minus 8y prime, so that's minus 8 times e to the 4x times 4 cos 3x minus 3 sine 3x, and then plus 25y plus 25 e to the 4x cos 3x. So this is what we get plugging our derivatives. Here's y double prime minus 8y plus 25y. Sorry, minus 8y prime. All right, so again, here's y double prime. And then minus 8 times y prime plus 25 times y. And we're hoping that this all simplifies to 0. Again, we can factor out the e to the 4x. Every term here has an e to the 4x. That's why I've been kind of factoring the e to the 4x every opportunity I get. I'll give myself even a little more space. This gives me e to the 4x times 7 cos 3x minus 24 sine 3x. And then here I'd have 8 times 4, so it's minus 32 cos 3x, and then minus 8 times minus 3 is plus 24 sine of 3x. And then from this last piece, we'll have plus 25 cos 3x. That's what we get when we factor out the exponential term. And now we just want to verify that these actually add up to 0. You see the signs going, right? Those add up to 0. And then what about the remaining terms? Well, if I take 7 cos 3x and I subtract 32 cos 3x, I get negative 25 cos 3x. Combine these. You see that those all add up to 0 as well. So what we're getting here is e to the 4x times 0. And that is 0, which is what we wanted to see, right? We wanted to see that this differential equation was satisfied. That y double prime minus 8y prime plus 25y, we wanted to check that this actually comes out to 0. Questions about this guy?
Not about this one, but about a different one. But I don't know if we have time in the
Yeah,
class.
I think we're getting a little bit close, right? So we end at 11:20. Is that right? Or 11:15? We might have time to discuss something quickly. There was one other thing I wanted to do today, lecture-wise. I wanted to show you guys separation of variables. We'll have to wait for Wednesday to do that. I have you guys till 11:20. We have 9 more minutes. So, Malin, I think we have time to do one more. What's up?
I was a little bit confused about problem number 10 on the homework. I did get like the first derivative and the second derivative, and I took that into like the function. But like from there, I kind of got confused with solving for like the x term.
I'll come back to this in just a second. Real quick, before I move on to number 10, are there any other questions about the solution here for number 6? The reason I'm saying is because I wanted to give you a hint, a nudge, that this is definitely the sort of thing you might see on the first test. All right, I give you a differential equation, I give you a function that I claim solves it, and I ask you to show me that it solves it. Or I give you a differential equation and a function and I ask you to check whether that is or is not a solution. Any questions about calculating y prime? It's all right if there are. If you need to go back over something here, now is the moment. Any questions about calculating y double prime?
No, thank you. That helps a lot.
Okay. Any questions about the algebra simplification of y double prime? Any questions about building the ODE and verifying that it's a solution? Okay, then we're going to go to Malin's problem, which was number 10. This is a great problem. The equation in question here is what's called a Cauchy-Euler equation, and this is some of the coolest out there. So they want us to find values of the parameter m such that y equals x to the m is a solution to that equation. Remind me at the start of class on Wednesday, I have a funny story about this problem. So find m such that y equals x to the m solves x squared y double prime minus 6xy prime plus 10y equals 0. So here the y double prime has an x squared, the y prime has an x, and the 0th derivative has just a constant. Equations of that sort are called Cauchy-Euler equations. As in the last one, the trick is to build the differential equation by taking the appropriate derivatives of the proposed function. So I'm going to calculate y prime, which is mx to the m minus 1, and y double prime, which is m times m minus 1 times x to the m minus 2. And then plug these in. Into the ODE, we get x squared times m minus 1 x to the m minus 2 minus 6x times m x to the m minus 1 plus 10x to the m. And this is all supposed to be equal to 0, so I'm going to put the 0 on the left over here. And what you notice is that the powers of x from each term are exactly what you need to bump these guys back up to x to the m. So this is m times m minus 1. Now x squared times x to the m minus 2 is x to the m minus 6m x to the m. Again, x times x to the m minus 1 is x to the m. And then plus 10 x to the m. So what I can do here is factor out the x to the m. And what will be left is m times m minus 1 minus 6m plus 10. The resulting equation here is, it might look like it's a polynomial of order m plus 2, but since x to the m, I can assume that this is not always 0, right? This would only be equal to 0 if x is equal to 0. So it's really this piece that's interesting. So let's clean this up. This is m squared minus m minus 6m. What I'll have m squared, and then minus m minus 6m is minus 7m, and then plus 10. And all of this is equal to 0. So either x to the m is identically 0, or this quadratic is 0, m squared minus 7m plus 10. If x to the m is 0, that's boring. It's only true if x itself is 0. And we want a solution curve, right? We don't want to just say, oh, this differential equation can only be solved if x is 0. And then in that case, we have the 0 function. That's boring. So we're going to go ahead and work with the quadratic here. Is this factor? Five and 2, right?
Yeah.
So this is m minus 5 times m minus 2, which implies m equal to 2 and m equal to 5. In other words, x squared solves that differential equation. If you were to plug y equals x squared in here, you would get a solution. And x to the 5, if you were to plug y equals x to the 5 into this differential equation, you would get a solution. These are the two values of m that do the job. Again, equations like this are very, very cool. We're going to have a lot of fun with them later in the semester. But for right now, we're just sort of practicing the basic mechanics of the objects in play. So are there any questions on this one? Okay, again, this would be a really appropriate test 1 level question. This is about the level question I could ask you on your first exam. There will be some other stuff that we haven't covered, but just difficulty and length wise, this is about test question length. I'm going to go ahead and wrap it up here for today, guys, because we really don't have time to talk about separation of variables. That's what we're going to begin with next time, and I'm not going to do any recapping next time. So we are into the semester. The drop date is passed, and well, the drop date is today, right? And so beyond today, we're just going ahead full steam. So please, if you're not into WebAssign yet, you need to get in today. Remember, even if you don't have your access code, you can get into WebAssign. You just use the trial access until your access code gets here. You need to be working on the homework. There's quite a lot of homework, and there's going to be more. So please don't mess around with this. Next time, we're going to talk about separation of variables. I have an office hour this afternoon from 3 to 4 p.m. If you need anything else, send me a message in Canvas or an email. Any last questions before we go? Alrighty then. Hope you guys have a lovely rest of your day. Don't be shy about asking for help if you need it. Otherwise, I will see you tomorrow morning. Bye.
Bye.
Have a good day, Professor.
You too. You too.